Hello and welcome to Danesh Academy. Today we're embarking on an exciting journey into the world of AirComp technology. Our mission in this video is to walk you through the captivating landscape where functions are effortlessly computed over the air. Stick around as we unfold the boundless possibilities and real-world applications of this cutting-edge innovation. Ready to explore? Let's jump right in. As we progress through this video, we will begin by uncovering the reasons why AirComp is absolutely essential. Following that, we will give a brief history of AirComp, and then in the third part, the fundamental concepts of AirComp will be discussed. Finally, in the last section, we will explore the challenges faced by this technology for over-the-air computation. In the next generation of communication systems, many services and applications have been defined which might need to compute a set of functions. To name a few, we can refer to sensing and edge learning over wireless networks. For example, in a wireless sensor network, we may be interested in receiving a summary of the measured temperature by the sensors over an area, rather than receiving individual data points. Or, in the case of edge learning, distributed devices with their own local datasets collaborate in training a machine learning model at the edge server, where the average of the received local trained models is computed. Typically, in these applications, participating devices first communicate their data, and then the desired functions are computed based on the received data points. In other words, in these systems, information communication and function computation are seen as separate tasks. In this case, the required data points are sent to a base station or an access point over a multiple access channel, where factors like fading, noise, and interference can affect its received signal. And then, once the transmitted data points are detected, they are forwarded to a fusion center or a computation unit for further processing the desired functions. A multiple access channel is a communication channel in which devices try to simultaneously get access to available resources such as bandwidth, time, power, and so on. To manage how different devices use these resources, multiple access techniques are needed. One approach is to apply orthogonal multiple access techniques, wherein devices are separated from each other in frequency, time, or space to prevent them from interfering each other as much as possible. However, when resources like bandwidth and time are limited, we turn to non-orthogonal multiple access techniques, where devices share bandwidths and time to make the most of what's available. Till this moment, an important question still remains that what actually is AirComp? AirComp is a technique in which devices transmit simultaneously over a shared frequency and time resource similar to non-orthogonal multiple access techniques. However, instead of separating communication and computation, it unifies these two parts by benefiting from superposition property of wireless channels. The other thing is that, in contrast with communication and computation separation, where we try to remove the interference between devices, in AirComp, interference is seen as a means of function computation over the air. Also, when communication and computation are separated, digital communication is mainly used, which is different from AirComp that uses analog communication. Going back in time, to the best of our knowledge, the idea of function computation over multiple access channels was first analyzed in the Bobek-Nazar's article in 2007. Later on, in 2013, Mario Goldenbaum made the first connection between over-the-air computation and a class of functions called nomographic functions. And 2 years later, he showed in another paper that AirComp can improve function computation rate more in comparison with separating communication and computation. Because of the inherent superposition property of waves over the air, AirComp is mainly suitable for computation of a specific class of functions called nomographic functions. A nomographic function is simply any function that can be represented as post-processed sum of pre-processed values. As examples of nomographic functions, we can refer to weighted sum, majority vote, polynomials, p-norm, and counting the number of devices belonging to a specific class. Let's break down the process of function computation with AirComp based on the definition of nomographic functions we talked about earlier. The input data points are first pre-processed with some specific functions, and then they are transmitted over wireless channels which are influenced by fading and noise. At the receiver, the received signal is then post-processed to calculate the output function. However, as can be seen, fading and noise are two destructive factors, so it is essential to tackle these effects by employing further processing units. For example, using suitable power control strategies, pre-coding techniques, and encoding the pre-processed data before transmission. Generally, based on the used encoding type, AirComp approaches can be categorized into two groups, encoded and coded AirComp. Encoded AirComp uses analog encoding and can be used for computing functions with continuous valued inputs. However, the coded AirComp deals with digital encoding and discrete functions. This makes it possible to use some sort of source channel encoding like the ones used in digital communication, which can further improve the reliability of system against noise. So, here is the whole view of an AirComp system. As you can see, the data is first pre-processed with a function and then goes through encoding and pre-coding units. And after passing through the wireless channel, the superposed signal is processed with a linear decoder such as multiple antenna receivers. Then, the received signal is decoded based on the used encoding method at the transmitters, and in the last step, we have the post-processing function which completes the computation task. Now that we get familiar with the fundamental concepts of AirComp, let's see what are some challenges in the past to implementing AirComp reliably. The first barrier is that most of the theoretical analyses are based on the assumption of the perfect channel state information and synchronization. However, in practical scenarios, imperfect channel state information and offsets in frequency, time, and phases are common and should be considered. Another challenge is about security aspects of AirComp. While it is true that in AirComp the individual data of devices is not shared with the receiver, there are still dangers that threaten the security of the system. For example, jammers can interfere the superposition and eavesdroppers can overhear the computation results. And finally, AirComp should be used for different computation tasks, and performance of the system should be measured by the metrics other than the commonly used mean-squared error. For example, one of the most potential applications of AirComp is in federated learning, where a model is trained in a distributed manner without gathering the data sets of each participant in a central unit. In this case, AirComp can be used for aggregation of the models at the receiver, so it is important to use better metrics that can suitably reflect the performance of the trained model and evaluate the system based on the specific objectives. Thank you for your attention to this tutorial up to this moment. We sincerely hope that the knowledge and insights you've gained from this tutorial have proven to be valuable for you. Also, we'd like to invite you to read our article titled Digital AirComp Assisted Federated Edge Learning with Adaptive Quantization for more information about the application of AirComp for federated learning. Until then, take care, stay curious, and continue learning with Danesh Academy.